All right, we're back. Hopefully I'll be able to put these two together and we'll get the first part of this lecture again. So we were talking about the difference between return and return I. Here we are. So return I versus return. They both do the same thing in terms of what they do to the stack. All right. What they do is they take the first 2 bytes off, they shove them into the program counter. What is not shown here that is kind of interesting is the status in the SReg of the I bit. Right? The I bit is the interrupt enable bit. So if we go back a little bit here, we're going along. Here's where it goes low. As soon as, now this is going to get set to 0F, we go up here to 2. Come on, jump to 2. There we go. As soon as we jump to 2, we turn off the interrupt bit. Then we go through this stuff. When we call return I, the interrupt bit gets set back to 1. This is a protection because what you do not want is one interrupt firing while you're handling another interrupt most of the time. There are cases where it happens and you do want to deal with that. But the default is to not let interrupts happen while other interrupt service routines are running. So that's why you need return I. Question?
So you're telling me you can't do an interrupt with an interrupt?
You can, but it requires manual intervention. All you would have to do is right here stick another SEI instruction.
Oh, okay.
Was that a question?
Yeah. When does the interrupt trigger?
The interrupt triggers, well, the answer is you don't know. It's external. It's this particular one that this example is showing is when this guy goes low. All right, we'll talk about how to configure that in the next slide. Okay, but when will it fire? Will it fire on this line or on this line or on that line? Actually, it will never fire on this line, but it will always execute one instruction after an SEI before it lets things fire. Okay. He's very impatient. We're going to move on if there are no more questions. He wants to know, what is this stuff? So it's a peripheral. External interrupts are peripheral. And we get to configure them just like timers. All right. They consist of external interrupt control register A. That external control register consists of 2 fields. ISC1 and ISC0. They do the same thing. They're duplicates, okay? And what they determine is, hey, when should the interrupt trigger? Will it trigger when it's low, on any edge, only falling edge, only rising edge? Okay, so you get to decide what event will trigger the interrupt. All right. That's not the only thing, okay? Oh, this is just a reminder. Don't do it like the book does it. Do it better. Instead of just throwing a 2 in, which is unhelpful, do it like this. Say, all right, I want 1 0 in ICS 0 That automatically tells you, hey, I want mode 2. What is mode 2? Mode 2 is falling edge. In fact, it's the same whether you're doing 1 or 0. The advantage of this is, well, so here I'm setting it into the MCU CR. That's for the ATmega32. It's called the, where did my pen go? The EICRA in the 328P. So just don't be confused when you see registers that don't exist in the 328P. It's probably for the 32. Okay. So do it like this. And do not do it like this. I see more people do it like that. I should just get rid of it. This is the best way. Do it the best way. All right. Makes it much easier to edit later because the bits that you need to edit are right next to each other. So the best way is just do it like that. And if you wanted to set both of them, then you would just add in a little bit extra. 0B11 shifted left by IS shifted left by ISC10. 10 is this bit here. So it'll take the 2 bits and shove it into that location. So what is that going to mean? That one line would mean that external interrupt 0 is going to be mode 2, or falling edge. External interrupt 1 is going to be mode 3. What's mode 3? It's rising edge. So every interrupt that you want to trigger is going to need some kind of configuration. We've already talked about how to configure the timer up to here. But this is the external interrupts. We got to configure them. Now, that's just the configuration. We still have to enable the interrupts locally. Okay, clear off all this ink. Configuring them locally. Oh, did I not? Where are my? I don't have it. I have the timer mask. But I don't have, well, I think we're going to have to make a quick jump over to the data sheet. I think that's okay, though. We'll take a quick jump over to the data sheet, which, by the way, anytime you are programming, anytime you're trying to attempt anything on the 328P, you really need the 328P manual open. All right, let's talk about that for a second. Let's just head over here. I want to do the desktop. Here we are. Minimize that. So here's the data sheet. If you want to deal with any kind of peripheral on here, it's usually a good bet to start by showing the screen here. Better. Okay. Start on the left on the table of contents here. Find, hey, external interrupts. External interrupts will have a few pages on how everything functions, and then it goes right into register description. If you want a shortcut to the register description, in the table of contents, you can always go to register description. It will show you all the registers. So we talked about the control register. Sets up what kind of a control you want. The mask register says, hey, okay, these are the individual interrupt vectors that can be triggered. We can trigger something called int0 or int1. You write a 1 to those bits to enable one or both. As we keep on moving down the list, we've got a flag register. So it is possible to use external interrupts without actually interrupting things. You just sit there and pull these flags. Okay? And we'll get to the last 3 in a minute. That's a whole different topic. But to do external interrupts, it's 2 steps. Set up your mode. Ooh, can I? Yes. What has happened here? What is? I can't circle. All right. Set up your mode. And that would be the mode for interrupt 1. Then turn on interrupt 1. Now, what does that mean? You've enabled interrupt 1, but how does that relate to external hardware? Well, to do that, we've got to look at our pin descriptions. So here's the 328P. All we have to do is find the pin called int1. And here it is right here, int1. So that means on a change in pin D3, something will happen. Okay, the interrupt vector will be called. So all of these things mesh together. We have to kind of pop back and forth around in the data sheet, and that's hard to do at the beginning. All right, but it's all related. All right, back to my slides, and that's good. And I've got to change the recording to screen 1. Excellent. Okay, we don't need to see that. We're past that. We're good with that. Okay, so here, let's move on to the timer. Unless there's more questions on external interrupts. We can go back to external interrupts. We want to talk about it. Okay, so here's timer 0. Things that should be familiar, stuff like this. This is just setting up normal mode delays. Put -32 into the free running counter, turn on the clock source bits, and normally we would have to poll. We'd have to poll for the flag. But what we're going to do here, well, no pun intended, what we're going to do here is we're going to read in from pin C and output to port D. That's all we're going to do. We're just going to sit in that loop. Whatever's on C, we'll send to D over and over and over again. The interesting stuff is what we've done here in red. This is our interrupt setup. We said, all right, we want to enable interrupt, i.e. enable interrupt, interrupt enable, the overflow vector. So when timer 0 overflows, a vector will be triggered. Vector is just a function. A function will be triggered. So with these two steps, we throw it into the mask register. And the second thing we do is we enable global interrupts. So you got to do both. You got to enable local and global. We got to configure our setup. We have over here at address 16, which happens to be the timer 0 overflow vector, okay, a jump to this function, which is over here in purple. So most of the time, we're just going to be sitting in this loop. We're just do. However, at some point, right about here, the timer is going to overflow. At that point, our execution is going to jump over to here. Then it's going to jump over to here. It's going to go all the way down. Then the return I is going to return to the next instruction. So it stops at 26. It returns to 27. The only thing that we've added is this part in red. The part in green you should already know about. Okay, this is just an interrupt service routine. What is it actually doing? Someone analyze and tell me what this is actually doing at a high level. Big picture here, what's happening? Toggling what bits? All of them? It's actually toggling one of them, right? 20 would be 0010, 0000. So exclusive ORing something with a 1 means that that bit will toggle. So how would you say what bit that is? This is bit 0, bit 1, bit 2, bit 3, bit 4. This is bit, it's going to toggle bit 5. A better way of writing this, again, would be to say 1 shifted left by 5. That way you just know, bit 5, done. All right. Which also makes it easier when you like screw up your wiring and you accidentally plug it into bit 4. You don't have to recalculate the hex in your head. You just change that number to 4. Okay. Okay, so timer 0 with an overflow interrupt. The setup is the same. It's just we add in that one thing, but we are freed up to do other things. This is other stuff. We can do other things. We don't have to sit there and constantly poll, which is super useful. So in lab 3, right, you're writing a delay function. Wouldn't it be nice if you could set up timer 0 to trigger every 4.16 milliseconds or whatever it is? And then just, you know, inside your function, you just update the time or you update the 7-second display. Meanwhile, you can do whatever else you want. You can recalculate things. You can be loading in from memory, doing whatever you need. But that would give you a very specific time delay because the timer keeps on running. There's no overflow involved or no overhead involved, except for the jump to the vector and the jump over to the function, which is what, 4 cycles. Much lower overhead. I think the next couple of clicks are just going to be me pointing out, yep, initialize the timer, initialize the interrupts. Here it is in C, same stuff. Oh, I lied. Oh, this is a compare match. This is the preferred way. Compare match is usually easier, especially for things that are cyclic in nature. Cyclic means happens over and over and over again. Normal mode is great for one shot. You want to delay once and then move on with your life. But cyclic, it repeats, is really good. So if you're trying to make a square wave, compare, clear on timer compare match is the way to go. And again, the only addition here is right here. We've just turned on the output compare interrupt enable bit in the TI mask register. This will require a little tweaking if you take this code and directly port it to the 328p because there's no TI mask register. It's TI mask register 0. Okay, but the bit names are good. Okay, so what we just demonstrated is there's two places that can cause interrupts, right? We've got external interrupts and we've got timer interrupts. What happens if at the same time the timer overflows, we pull that pin low? What interrupt do we service? How would we even decide? Can we service them both at the same time? No, we've only got one CPU. We can only execute one instruction at a time. Well, we need to have a way to decide, right? Well, the CPU designers give us a priority. The closer you are, your program address is to 0, the higher your priority. So in the case where pin D2 changes at the same time as timer 0 overflows, which one would occur? Interrupt 0 would happen first. And the way that it would work is when interrupt 0 fires, it goes through, it does a return from interrupt. At that same time, right when we return from that interrupt, we then get called to the timer interrupt. So it's not like you miss it. It just gets delayed. Okay? So the interrupts will happen and be serviced in the order of their priority. Yes?
Now, is it putting it in the stack after, or are they putting them both at the same time and then doing it? Or does it do it and then put the next in the stack?
So the way it would work is it would trigger interrupt 0, put the return address on the stack. Then it would go to the vector. It would service that vector. The return I would happen. And I'm going to tell you that I'm not sure if it pops that off the stack or then interrupts right at the return. I think it would have to come back, execute one instruction, and then trigger the next interrupt, put the return address on the stack. I think one instruction gets executed. The reason I think that, if you look at the documentation for SEI, SEI is the instruction that turns on the I bit in the status register. You are guaranteed to execute whatever the next instruction is before an interrupt happens. So that would, to me, indicate that the I bit has to be active for at least one cycle. So when you do a return I, it would execute one instruction. But it would be easy enough to test that just in the simulator, test out what happens. And I'm sure if you read the data sheet, it would tell you what would happen. The answer is almost always in the data sheet. Do I remember off the top of my head? No. And again, the I flag needs that return I instruction in order to work, because otherwise interrupts are disabled. When an interrupt happens, the I flag is disabled. All right, so moving on to a gotcha, a trap for young players, as some people would say. Here we've got some code, and we've got some basic code. It's got an interrupt for the timer, compare match. We set up our stack pointer. We do some I/O setup. Okay, it looks like we've set one bit to output. We've configured our output compare register. We've configured this to be CTC mode. We've turned on our interrupt enable. What else do we have here? Output DDR to C. Okay, so more I/O setup. And then we've got this loop. So here's our low priority loop that can get interrupted. Effectively, what we've done is, okay, when we get an overflow, or when we get a compare match, rather, we're going to service this interrupt routine, which just takes whatever is on the pin D, increments it, and sends it out again. So what we should see on port D is 0, 1, 2, 3, 4, etc. FF 0, 0, 0, 1, etc. All right. Now, each one of the pieces of this works as intended. Okay. This part right here is just saying, hey, take whatever is on port C, increment it, and output it. Right. It loads up so on port C, we're going to see 0 and 1 and 2 and 3 and 4 because we're just incrementing R20, R5, 6, 7, blah, 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 FF, 0, 1, 2, 3, and so on and so forth. This loop is perfectly syntactically correct. This loop is perfectly syntactically correct. All of our outputs are set up. Interrupts are firing. I can watch port C increment. I can watch port D increment. Unfortunately, it does not give me the sequence that I've described on screen. Okay, the reason is very much hidden. Okay, and it has to do with Murphy's Law. Murphy's Law says that anything bad that can happen will happen at the worst possible time. Give you an example. I went up to Maine to do a sensor install, and the first thing we had to do was do a couple of things on my computer first thing in the morning at their field office, and then we were going to drive like 45 minutes out into the wilderness to install these sensors. So I open up my computer, and what do I see? No, worse.
Black screen.
Battery.
Nope, battery's fully charged. I checked everything last night. I see on the screen. Don't worry, we're updating your computer. But everything will be right where you left it. And it did that for 2 hours. And meanwhile, we're paying people to just sit around. So Murphy's Law, anything bad that can happen will happen at the wrong time. So the title of the slide may give you a hint. Does anybody see any resource conflicts between this loop and this function? R20 is shared between these two functions, between these two pieces here. This is a problem. This is a problem, right? Because this is going to be incrementing every 4 or 5 cycles, right? 1 cycle here, 1 cycle here, 2 cycles there. So it's going to be incrementing every 4 cycles. How often will this R20 be incremented? How would we calculate that? Well, we calculate it because we're in CTC mode. That means that this is going to overflow, or it's going to trigger every 161 cycles, right? Because we're just doing timer with no prescaler. So it's going to go 1, 2, 3, 4 until it's done about 160 cycles, which would be what? Well, we do 1 every 4, so that's about 8. It would get up to about 80 decimal, right? That would be 4 times 80 is, no, it would be 40, right? Arithmetic isn't my strong suit. 40. 40 times 4 is 160. It would get up to about there, and then the interrupt would fire. And what would happen? Whatever is on pin D will overwrite it. And chances are what's on D? Not 40, but 0. Then it will increment that to 1. So you'll see 1 on port D. And then this will begin incrementing again. 2, 3, 4, 5, and it might get up to 41 this time. And then the interrupt will fire. And what's on port D? 1. So then we'll get 2. So this is a problem. How do we solve this problem? We encountered a similar problem when we first started talking about registers, right? When we said functions use the same registers, we came up with 2 different solutions. The first was just use a different register. Done, fine, okay. But we said that wasn't a good solution because eventually you do run out of registers. So the better idea is to do what's called context saving. You save the register. Anytime you use a register inside of an interrupt, if you're writing an assembly, you should push it and pop it at the end, just like any other function. You should always context save. But this isn't the really dangerous one. This one is relatively easy to spot. Where things get really big is when we get into conditional jumps. Why is conditional jumps a problem? Let me give you a very basic idea. We say with an ink here. Yeah, yeah, there we go. So we say CP R16, R17. This sets maybe the Z flag. And then we do a branch if not equal to task. Well, Murphy's Law says that anything bad that can happen will happen. So you'll execute this instruction, you'll set the Z flag, and then an interrupt will fire. You'll go down to your interrupt, and you'll do some adds, R5, R6, and then you will return from your interrupt. Well, I hate to break it to you, this sets the Z, the C, the H flag, whatever it sets. It sets all of these things. Or maybe it clears the Z flag, right? So here, this instruction, whatever's in R16 and R17, causes the Z flag to be set. Down in the interrupt routine, you clear it. So you compare, and that says, okay, you're going to branch. Or rather, it says you don't branch. So normally you would fall through. But the interrupt fires right here. So this clears the Z flag, so now you do branch. Well, how the hell do you save that? Well, it's actually not that hard. All you have to do is save the status register before you mess with it. This is how you do it. You save it, you push R20, because you're going to modify R20 inside the routine. Then you get the status register into R20, and you push R20 again. So what does the stack look like? First, you put whatever's in R20 in here. Then you put whatever's in the status register on there. Now on top of that is your return address. Okay, so you have to make sure that you get all this stuff off the stack. So the first thing you do is you pop into R20. So status register goes into R20. And then you output that to the status register. So now the status register has been just restored from whatever it was. Then you pop the next thing into R20. And finally, you'll do a return or a return I, one or the other. And that will do the return address. So saving the status register, not so important for functions, but very important for interrupts. Okay, how are we doing here? Good. So the remaining part of this is just talking about it in C, okay, which is easier. The assembly is harder. Now, I said that regardless of whether you're doing it in C or assembly, you needed 4 things, but they were different sets of 4 things, okay? The 4 things you need in C, first, it's the same. You need to enable global interrupts with a function called SEI, which looks exactly like the assembly instruction SEI. In fact, there's an SEI function and a CLI function. Now, they're actually function like macros, but they look like a function. Second thing you need is you need an interrupt service handler. Okay, you need a handler in assembly too, but it's a little bit different. To make it a handler, you say ISR, open parenthesis, close parenthesis, and then you put a special name. Special name. The special names are looked up in the C language database, but here they are. Things like int_0 vect, timer 0, compare a, vect. They all end with _vect. Okay, that automatically takes care of some of the stuff in assembly. The third thing you need is you need this include file. Okay, this include file tells it what that thing is and what that thing is. It also tells it what SEI is, actually, now that I think of it. Okay, you need that include file, avr/interrupt. The fourth thing that you need, I don't highlight it. The fourth thing that you need is you still need to locally enable. So 3 of the things are the same. You need to globally enable, locally enable. You need to have a handler, although the handler syntax is a little different. The fourth thing is different. You need the interrupt.h file included. Okay, let's keep going here. Okay, so here, so this particular one used normal mode, and it toggled some pins. Here it is using CTC mode. And again, I hate this kind of syntax. It's terrible. You should say WGM02, 1 shifted left by, ORed with, goodness gracious, I'm having a little bit of difficulty here. ORed with 0B001 shifted left by CS00. Parentheses are important. You got to put those in order there. Much easier to see and understand what's going on. Okay. Now, there's one kind of interrupt that I have not talked about called pin change interrupt. Discard ink annotations, go over to open board, and switch this all around. So one kind of thing we didn't talk about, on the explained mini board, you have a button, and it would be really nice if that button could trigger an interrupt. Unfortunately, there's only 2 pins that allow interrupts, D2 and D3. Those are external interrupts. And let's go over to desktop. So D2 and D3 are the only interrupts allowed. Eraser. Now, one of the nice things about the 328P series as opposed to the 32 series is almost all of the pins can do what's called pin change interrupts. So there's only 2 external interrupts, but just about everything can do a pin change interrupt. Am I recording the right thing? Yes, I am. Okay. A pin change interrupt gets a little bit more complicated, though. First off, I want to show you that I want to highlight. Where's my highlighter? Do I not have a highlighter? Area highlight. Here's port B. Ooh, can I do it in different colors? Oh, this is a bummer. I wanted more. All right, let's do it like this. Here's port. Once again, my pen doesn't work. It's like it doesn't know what screens to do. All right, that works. Okay, port B. Oh, shucks, port B. Just going to erase and start again. Just going to erase and start again. Oh, I have to erase the whole freaking thing? Just erase everything. Okay. Okay, one more time here. Port B. Port D. And port C. All right, there they are, huddled together. And if you follow along with what the pin changes are, port B is in 0, 1, 2, 3, 4, 5, 6, 7. Port C is 8, 9, 10, 11, 12, 13, 14. And then D is 16, 17, 18, 19, 20, 21, 22, 23. So 0 through 6 is B. Sorry, 0 through 7 is B. 8 through 14 is C. And 16 through 23 is D. So roughly, they're divided up equally into groups of 8. So then I want to go to the pin change interrupts. All right, and there's actually a few different registers associated. First off, there are 3 different interrupts that can occur. Pin change 0, pin change 1, pin change 2. This is different from external 0 and external 1. They're totally different. Okay, there's a flag register. These flags get set when one of those interrupts occurs. But then there are more configuration registers. Normally we just deal with the interrupt enable and we'd be fine. But here we have 3 registers. They correspond to 23 down to 16, 14 down to 8, and 7 down to 0. Which just so happens to correspond to interrupts occurring on B, C, and D. So if you want an interrupt on any pin anywhere, for example, pin B7. Let's try B7 because it happens to have a button on our trainer board. Okay, so B7 would correspond to this pin, okay, PC-int7. And if we wanted to do that, we would have to put a 1 in this bit, and because this is PC mask 0, we would also have to go up all the way up here into the interrupt enable and put a 1 here, okay? So this bit says that any of these 8 sources could trigger. But because we only put a 1 in this bit, it means only a change on B7 will trigger an interrupt. If we had put 2 1s, when the interrupt fired, we wouldn't know which bit was triggered. We would have to do some testing inside of the service handler. We'd have to look, say, is this guy 1 or is this guy 0, in order to determine what's going on. Now, the problem with the pin change interrupts, okay, pin change interrupts, let's see if I have a little bit of description here. Here are our external interrupts. We can generate on low, on any change, on falling edge, or rising edge. We can mask off different types of events. On the pin change interrupts, it is always any change. Always. It will always be any change. So in your lab for lab 4, I give you some sample code that basically says inside your ISR for, say, PC-int0 underscore vector, you might want to say, hey, if pin B ANDed with, it's important to put parentheses here, pin B and 1 shifted left by 7 equals 0, this would be, oops, wrong direction. This would be falling edge, falling edge. Then you could do some stuff for the falling edge. Else, this would be rising edge. And then you could do something else here.
Now here's the thing. You said if you need to handle it, if there's already 2 1s, like if there's 1 the first bit compared to the last one.
Yeah.
But that's only assuming that.
That's only assuming one of them is on. Right. It gets more complicated.
2 of them on.
If 2 of them are on.
Which one is? But
for today, I'm going to pretend like we just have 1 because we only have so much time in the day.
Okay.
Although, what do we know? We have till 10:45, right? All right. So that's actually, we're in pretty good shape here. So, pin change interrupts are always any edge. All right. And that's where we're sitting right now. Now, let me just take a check. I did not expect to be done this quick. We're actually in pretty good shape here. I want spring. No, we're in fall 17. Topics. Let's just check on this here for a moment. Is Mr. If you ask me to regrade your exam, I have that. So today, here we are on October the 17th. October the 17th. So here we are on interrupts. We're doing pretty good. But this coming Thursday, we do start the interrupt lab, which means your TDM lab is due. Okay, let's look at the interrupt lab. But before we get to the interrupt lab, we gotta. So excited. That joke, it's joke time. It's a knock-knock joke. Who wants to be my guinea pig? Yep, there you go. You want to fold your arms and look like you're too cool. All right, okay. Knock, knock. Interrupting cow.
No, this one.
Boo! Yes.
There's more, right?
Note who shall give Clark a 0. Don't get your. Okay. It's my favorite joke.
That's a good one.
Oh, now I love it.
That's a joke I remember using it when I was a kid.
But it's the class on interrupts, Scott. Fine, I won't help you with your lab. What do I care? All right, let's look at the lab. Guys, they're so mean to me. You know, I try and I try and I try. Okay. The interrupt lab. The interrupt lab actually mostly is just a rehash of lab 3. Okay. You're going to be using some pin change interrupts, and it splits up the lab into a couple of phases. Each phase should probably be its own project that you can put code back and forth between, so you can always go back to code that you know works. This, by the way, is the way the datasheet is going. If you download the datasheet these days, Atmel was recently bought by Microchip, so they're revamping all their data sheets. So it gives you a rundown of here's all the pin change stuff, and it says, hey, make a pin change interrupt, and it gives you almost all the code. It says, okay, here's pin change interrupt 0. Here's how we enable a pin change, okay? And this says, hey, you're going to do a pin change on pin 0, pin change interrupt 0, which corresponds to B0. Okay, you might want to modify this code a little bit. See, here we make B0 an input. Here we turn on a pull-up resistor. So maybe you want to do a different pin, maybe not B0, maybe B7. So you would have to modify this code to deal with B7. Close this so I can get a little bit more here. So that's one thing you might want to do. All right. And it doesn't give you any code like what do you do inside the interrupt? I don't know. You can make it up, or you can read the lab. It does give you some information on how you might test if it's a rising edge or a falling edge, because if you have a button press, when you press that button, the device is going to go low. You're going to see a 0 volt. And when you release the button, it's going to go high. Now there's going to be an interrupt that gets triggered here, triggered there and there. You only want to trigger an interrupt once per press. So to deal with that, you can use some kind of code like that. Now, on Thursday, we're going to talk about another peripheral called the analog digital converter. Its whole job is to get some data, okay? I'm going to let you read this on your own, and we'll talk about it on Thursday. There's some math involved here. It's not particularly complicated math. It's division, okay? It tells you all of the vectors you are likely to need, all right, along with a few that you might not. This is one thing about interrupts that I don't normally talk about until the lab. The bad ISR vector. It is already defined for you in C. We saw it when we compiled the C program. There's this bad ISR. But you can overwrite it so that you can put a breakpoint. You'll put a breakpoint right on this line. So if you accidentally trigger an interrupt that you didn't mean to, you will get instant feedback. You'll say, okay, I triggered a bad interrupt. Let's figure out what happened. All right. So I recommend you throw that into your code anytime you're using interrupts. The big trap in C for interrupts, where did my mouse go? Okay, is the idea that the idea of scope. All right. An ISR, all right, cannot return a value. There's no return type. There's no int. There's no int return type. It has no return type. So how do you get data out of an ISR? Well, the answer is you go against every bone in every CIS course that's ever been taught. You use global variables. So you just make it global. You say everybody has access to it. The scope is everyone in the file can see this variable. And that seems like it would work because it'll at least compile, because it knows that Bob is a global variable. So if you say Bob equals 10 inside the interrupt service routine, it'll get assigned. The problem is the compiler is the dumbest smart thing you've ever seen. And it doesn't understand that if you use Bob in the main program, Bob equals 5, Bob plus plus, and then down here you say Bob equals 0. When you press the button, the interrupt service routine will fire, okay? You will never see Bob equal to 0. It will never get reset unless it overflows. The reason is because the compiler looks through and says, okay, this line's going to execute, then this line's going to execute, then this line's going to execute, then that'll execute, then that'll execute, then that'll execute. Oh, this is a loop. And it will say, oh, this just lives here. So what it's going to do is it's going to say this is permanently going to be in a register, R7. This is going to say, oh, Bob is really address 100, let's say. All right, so it will modify location 100. And this here, this will load up from location 100, the number 5. But it never goes back to memory to check. This is what's called caching. It basically just assumes that it's never going to have to reload from memory. And that's a good thing most of the time because going to memory takes more time. So if you can cache it in a register and it just stays in the CPU, more is the better. So in order to deal with this, anytime you have something on the left side of an assignment inside of an ISR, when you declare this, you want to declare it as not just, say, uint8_tbob. You want to declare it with a special, my mouse is gone. There we go. Called volatile. Volatile. Okay, volatile says never cache this. It will always go to memory, which is important. It does mean that your program will run slower because it will never assume that it can keep it in a register. However, the benefit is your program will work. So that's something to keep in mind. So if you are using an interrupt and you have some variable on the left side of an assignment and it's global, you must declare it volatile.
Now, is this for interrupts or for functions also?
Just for interrupts. Because functions, it's smart enough to see that if you call my function, that's in the line of things. So it says it's going to execute this, then it's going to execute this call. Oh, that function is over here. So it's going to execute these lines and then return back to that.
Yes.
So the static analysis is smart enough to see that function. But there's no call to an interrupt. I really hope that I can erase all of this writing on this document. Okay.
Also, one more thing. You want to for the lab, you want so if the interrupt happens in any edge, why not just make it on falling edge if the button's going to make it on falling edge? Like, why do that if statement and why do that? Why just make it?
Because you weren't listening half an hour ago, George. Pin change interrupts are, it's a good question. It's a valid question, but I did tell him. Pin change interrupts are not the same as external interrupts. External interrupts can be configured to accept low, rising, falling, or any. These are pin change interrupts, which cannot be configured. They will always accept any. That is okay. Okay, timers. I think we've covered timers today. Again, if I see you, I'm just going to say this as politely as I can. If I see you doing things like writing 9 to TCCR0B, I'm just going to fail you on principle for the day or something. Okay? Please make use of the fact that you can say things like 0B001 shifted left by CS00, ORed with WGM02, or 0 shifted left by WGM02. I gave you 2 or 3 classes ago code that you could use in every project ever, and it would always work. You just had to tweak these numbers right there. Okay, so when you're programming this, please be aware of that. Now, there is a helpful website that I use when doing my timer calculations. It's the first Google result if you search AVR timer calculator. Okay, and here it is. And it is an extremely invaluable tool. Somebody wrote it in JavaScript ages ago. Hopefully I have internet that I can show this to you. Okay, all you do is you tell it what your clock frequency is and what the resolution of your timer is. And then you can configure a bunch of stuff. So if you wanted, for example, to do 240 hertz, you wanted it to fire 240 times a second, you'd type 240 here and click on the new frequency button. That'll recalculate everything else. And it tells you that you need a total number of ticks equal to 66,666.66, which obviously is not going to fit in an 8-bit timer. So it tells you, hey, that's going to overflow 260 times, and then the remainder will be 106 ticks. So that's not going to work for us. What you can do, however, is you can recalculate using different clock dividers. So say we had to divide by 8. Well, that's still going to overflow 32 times. Suppose you had a mouse that worked. If you divide by 64, that still overflows 4 times. If you have a divide by 256, that still overflows 1 time. So if we divide by 1024, okay, that's 65 ticks. Overflows no times. So that will fit in an 8-bit timer. The question is, what will we get as an actual frequency? Well, we can just say, all right, suppose we have exactly 65 ticks. Let's recalculate based on that. For whatever reason, there's some bug in there. It does calculate the real time correctly, but it says undefined for the frequency. So if we click on the real time button, though, it says, all right, that's 240.38 hertz. It just does the simple math, but it does it really fast. Okay? So 240, that's faster than 240. It's a little bit, not by much, but close enough. And because this is a persistence of vision, a little bit faster isn't going to hurt us. Now, what does that mean? Does that mean that you put 65 into the OCR register? No. It means you put 65 minus 1 into the OCR register. Always, whatever number you get out of this calculator, you want to do 65 minus 1. Okay. Now, the other option is we could have used timer 1. That's a 16-bit timer. And we could have tried this again. So let's try for 240 hertz. That still overflows by some. So we could try to divide by 8. And that gives us 8,000. Okay, so now we could do it with a divide by 8. And if we then did the same thing, calculate real time, we're even closer to 240 hertz. We're only off by a very small margin there. So that would be fine too. I don't remember if in the lab I say you got to use timer 0 or timer 1. Everything would change though, because you'd have to change what your interrupt enabled bits are, what your vector is, all that kind of stuff would have to change to match up to be timer 1 interrupts. Okay. So that's something you definitely want to look at. There is insufficient memory or disk space. Word cannot display the requested font. Okay, sure. So here I give a couple of examples. You should get used to doing this kind of math by hand, figuring out what your periods are, because I think we did it last class as stoichiometry, put timer ticks and system ticks. So here's the recommended approach. Phase 1, just create a program that fires an interrupt every 4 milliseconds and toggle some bit. That's all. That's the whole phase. Make sure that you can make an interrupt fire. Look at it on the scope. Make sure that, yes, it really is every 4 milliseconds, okay, using the timer. That's phase 1. Okay, and then to make sure that it works, look at it on a scope or on a logic analyzer. Okay, phase 2 is put a push button to that. So when you put a push button on, okay, the interrupt for pin change fires. And just have a variable called num2display. Okay, and again, I put a caveat here. Hey, it's going to fire twice. Make sure that it only increments once per button press. Just look at it in the the debugger. Okay. Oh, and I guess in phase 2, I also add. Oh, okay. what I actually did, when I wrote this, the phase 1 actually has a little bit more. I wrote phase 1, just toggle the pin. Then I kind of did a phase 1.5. All right. Once you've figured out that you've got a timer that executes every 4 milliseconds, add in code for the 7-segment display, because you're going to reuse the 7-segment display for this lab. All right. And it shouldn't be too hard. You just make an array in C now. You don't have to deal with any of that LPM stuff, none of the shifting to the left. Okay. Handle it from there. Then phase 2 says, all right, now when you have a button press, add 1 to the number you're displaying and watch it occur on the 7-segment display. Phase 3 we'll get to in week 2, because we're only going to be talking about the ADC on Thursday. But the ADC just says every time you press a button, read from the ADC and display the corresponding value on the 7-segment display. Okay. You will need to generate a flow chart. I want things like a hard copy of your assembly or C. Yeah, that's a typo. That should be C. You're going to do this lab 4 in C. Okay. Procedure connected up to the WaveGen and so forth. And the programming assignment is phase 3. So I say don't start with the programming assignment. Start with the different phases. All right. You can do everything except phase 3 now. Okay. We know about interrupts. We know about time division, multiplexing. We know about all that. So any questions? All right. Again, if you ask me to regrade your exam, I've got it up here. Otherwise, I will see you on Thursday. And I'll see about getting the rest of this video stuck together so that maybe it'll all go together.